Hi everyone, welcome to this session on Calico Security Policy Best Practices. My name is Adil Abdul Majid. I'm a solutions architect with Tigera's customer success team, helping our customers deploy Calico solutions. Okay, let's start off with the agenda for today's session. We're going to be looking at security challenges in Kubernetes and how Kubernetes disrupts traditional networking and security paradigms. We'll look at Calico security policies, the anatomy of a Calico security policy, and the declarative policy language. Next, move on to best practices for security policy implementation with some example security policy patterns. I think one of the best ways to understand security policies is to look at some examples and how those examples can be incorporated into your environments and build a security policy model. Once we have the model built, we will then look at how you can introduce policy governance to that policy model. Let's have a brief look at the Kubernetes networking model. The model stipulates that pods can communicate with all other pods on any other node without the requirement for network address translation. Agents on a node such as system daemons and kubelet can communicate with all pods on that node. And the most common container runtimes use container network interface plugins to manage their networking and security capabilities, Calico being one of the most widely adopted CNI plugins for Kubernetes. So at a high level, the Kubernetes networking model provides for a flat network where pods in the cluster can freely talk to each other. There are benefits to this model. It alleviates the complexities that could have been due to the underlying network. However, the model also introduces certain security challenges. Kubernetes disrupts traditional networking and security paradigms. In traditional networks, when security is enforced, it's done so at certain choke points in the network. And controls are enforced when traffic traverses or transits those choke points, typically using some form of networking construct. Now in Kubernetes, pod scheduling is dynamic, IP addresses are ephemeral, and scheduling is typically non-deterministic. Okay? What that means is you can't bind a workload identity to a networking construct anymore. Also, firewalls external to the cluster cannot map IP addresses to workload identities. So when traffic egresses the cluster, upstream firewalls cannot enforce security policies based on IP addresses because the IP addresses for a pod are non-deterministic. With those challenges also comes an opportunity, and we'll look at Calico a bit in this slide. Calico, among certain other functionalities, primarily offers the container network interface for Kubernetes, IP address management, and the security policy engine. Now, Calico is quite flexible in the routing modes that it supports, as well as the data plane it supports for policy enforcement. So for routing, you can choose between IP in IP, VXLAN overlay modes, or native BGP. And for the data plane, you can choose between eBPF, IP tables, and Windows HNS if you have Windows nodes in your clusters. Now, the primary benefit of this tight integration with the orchestration plane being that workload identity is tightly coupled to networking and security in a way that was never before possible prior to Kubernetes. And this offers a number of advantages that we will explore in the subsequent slides. Okay, so let's have a look at the anatomy of a Calico security policy. So a security policy has a scope. It could either be a namespace scope policy, which applies to a specific namespace, or a global network policy, which could apply to multiple namespaces, or even all the workload endpoints in the cluster. Now, there are a few selector options. You could use endpoint labels to select specific workload endpoints. If it's a global network policy, you can also use namespace selector to limit that global network policy to specific namespaces. You could also use service accounts as selectors. Now, a policy is going to have one or more ingress and or egress rules. And if you look at a particular rule, in a rule you could have either an allow, deny, log, or pass action. And in an egress rule, if you look at the destination, There's a to field there where you could specify the destination and the destination protocol. There's also a from field there that you can use to specify the source. Now, when specifying the source, again, you can use endpoint selectors or namespace selectors, service accounts, could be networks, network sets, or global network sets. Now, network sets and global network sets are a way of grouping either IP addresses or CIDR blocks, and we'll explore some examples in the subsequent slides. When it comes to protocols, again, we looked at some protocols in the previous slide. For example, you could choose between TCP, UDP, ICMP, even HTTP match if you're using layer 7 policies. All right, so quite a bit going on here, right? Just park this for the moment. I think we'll be able to bring this together when we look at the examples in the subsequent slide. But the idea being that there's a lot of flexibility within a policy, and understanding some policy patterns is the best way you could approach implementing a security policy model for your environments. Okay. All right, best practices for security policy implementation. So you should look at grouping all the rules that apply to a given workload or a group of workload into a single policy instead of having multiple security policies. So inside the policy, you can have one or more either ingress and or egress rules, and you should look at using rules for a given workload or a group of workload and making sure that you have a single policy for those workloads with multiple rules. Okay. Implement a hierarchical design that allows for optimizing the number of security policies by filtering out non-compliant flows at the top of the funnel. When we look at the policy model in subsequent slides, you will look at how, for example, global network policies are used to implement certain high-level controls so that we can filter out unwanted or non-compliant flows at the top of the funnel. Use global network policies to implement high-level guardrails and network policies to implement fine-grained controls. Okay, so global network policies are what spans across multiple namespaces or even all the workloads in the cluster. So you could use global network policies to enforce high-level security intentions and network policies for fine-grained controls that apply to very specific workloads. Leverage policy order with allow and deny actions when developing security policies, right? This is a powerful capability in Calico policies. Also use network sets and global network sets to group IPs and CIDRs so that they could be referenced by even multiple policies. Okay, it's just a bit more efficient doing it that way, right? So with these best practices in mind, let's look at some example security policy patterns. Now, the cluster shown here will be used as an example to demonstrate certain security policy patterns. This particular cluster has 2 tenants, and a tenant is simply a logical isolation. So it could be any form of logical isolation. For example, in your environment, it could be a PCI environment that you'd like to isolate from the rest of the cluster workloads. If you're a hosting provider, a tenant could be a customer. So if you have multiple customers, you have to make sure that they remain isolated in a shared cluster. Also, if you're having a shared cluster that's shared between various development teams, you may want to have a logical isolation, all right? So a tenant is any form of logical isolation that you'd like to create for your cluster. Now, a tenant could have one or more namespaces. So for example, in this cluster, tenant 1 has 2 namespaces, Shop and Yaobank, and tenant 2 has a single namespace called Bookinfo. Okay. Now the applications in these tenants are exposed using an ingress controller in the ingress nginx namespace. Right? So hopefully this cluster is similar to your environment. Of course, you could horizontally scale, you can have more tenants, more namespaces, but the pattern hopefully is similar to your environments. Okay. All right. So now let's look at some example policies. Before we implement policies, I'm kind of assuming this is a live production cluster, so I don't want to break anything, and that's why I've started off with a default allow here. And the default allow is simply a policy that allows all traffic. Now remember, in Kubernetes, by default, Kubernetes has a whitelist behavior. However, once you've matched pods in a policy, there is a default deny behavior, okay, an implicit deny behavior. Now I'm using this default allow as a failsafe so that I don't impact any live production traffic in this cluster, okay? So my first policy is a deny list policy, and the deny list policy is a Calico global network policies which applies to all cluster endpoints. Know the reason for that default allow. So now I have a policy that applies to all cluster endpoints. What that means is all cluster endpoints now have a default deny behavior for egress traffic, since this policy matches egress traffic. Okay, so this policy has an egress rule which denies traffic to IPs and CIDRs in the IP deny list global network set, and I've shown the global network set on the right hand side as well. Now recall that global network sets are a way of organizing, could be IPs or CIDR blocks, and referencing those in policies. Now the selector field is used in the egress rule to match the global network set based on the GNS equals IP deny list label. So if you look at the global network set, we have a GNS equals IP deny list label, which is referenced in the egress rule implemented in the security policy. There's also a namespace selector in the security policy, and the namespace selector uses a global match criteria, and that's because this particular network set is a global network set. Okay. So what this policy does is, if any of the cluster workloads try to connect to the IP addresses specified in this global network set, those flows are going to be denied by this policy. So for example, if you could retrieve these IPs from a thread feed and update the global network set, then you could effectively deny all cluster workloads access to those malicious IP addresses. Okay. Now, if you look at the actual underlying policy implementation, the policy is implemented for every endpoint in the cluster using the data plane. Okay. However, for simplicity, I've grouped all the endpoints and shown that traffic is denied to the IP deny list global network set. Okay. All right, so this is the first example. Let's move on. The second example is the kube-dns policy. So if you look at this policy, this is a global network policy. And in the ingress direction, the destination is kube-dns. And we've allowed UDP port 53, so the protocol is UDP. If you were to kind of visualize this policy, you have a kube-dns endpoints, and we've created this pinhole on the ingress direction from all cluster endpoints to kube-dns. So we've matched all cluster endpoints by using the namespace selector with the all match operator. Now on the egress direction, the source of the egress rule again is all cluster endpoints, and the destination again is kube-dns on port 53. So on the egress direction for all cluster endpoints, we've created this pinhole permitting traffic if it's destined to kube-dns on port 53 on UDP port 53. Again, recall that the pinhole is in fact created for all endpoints in the cluster. However, for simplicity, I've grouped those endpoints and shown a single pinhole. So this is the kind of visual representation of this policy. If you'd like to kind of visualize what the policy looks like, and this would be it. And this policy is quite powerful, isn't it? You now have a single declarative policy that's protecting all DNS traffic in the cluster. So you may have thousands of pods and thousands of DNS flows in the cluster that are now protected by this single policy. Okay, let's look at the next policy. This policy is called Tenant 1 Restrict. So this is the Calico Global Network policy which applies to all cluster endpoints in Tenant 1. The namespace selector field is used in the security policy with the project calico.org/name label to select endpoints in the tenant1 namespaces. Has an ingress rule which denies all traffic except from the specified namespaces. Has an egress rule which denies traffic except to the specified namespaces. And the not selected field is used in ingress and egress rules with the project calico.org/namespace label to exempt endpoints that should not be denied. Okay, so this is a global network policy, and in the policy, the namespace selector is used to specify the Hipster Shop and Yao Bank namespaces. So this policy applies to the Hipster Shop and Yao Bank endpoints. In the ingress direction, there's a deny action. However, the not selector is used to exempt the endpoints that should not be denied. Similarly, in the egress direction, the action is a deny. Again, the not selector is used to exempt endpoints that should not be denied. Now, the project calico.org label is a label that can be used to identify namespaces and endpoints in those namespaces. Now, the value of the label is the name of the namespace. So you could use the project calico.org/name key with the value of the namespace, and Calico will then select all the endpoints inside that namespace to scope the policy or the rule. Okay. Now, the project calico.org name label is something that can be used to specify or select endpoints. It's a label that Calico associates with an endpoint, and the value of the label is the name of the namespace that endpoint belongs to. Okay. So since we're using a not operator, we're using the project calico.org/namespace label, and we're providing the name of the namespace so that those endpoints are exempted from the security policy. Now, if you want to visualize this policy, we have the tenant1 endpoints selected using the namespace selector. So basically endpoints in Hipster Shop and Yao Bank. All traffic to other endpoints are denied except for what's exempted using the not selector. So this policy does not permit any traffic, right? Given that you've specified a policy for tenant1 restrict, a subsequent policy must permit traffic flows that should be permitted for tenant1 workloads. Okay, all this policy does is it isolates the tenant1 workloads and denies traffic to all other cluster endpoints except for what's exempted using the not selectors in the rule. Now we're going to have a similar policy for tenant2 as well. Again, a global network policy using the namespace selector with project calico.org/name label to select the tenant2 endpoints. Has ingress and egress rules, again with not selectors, using the project calico.org/namespace label to exempt endpoints that should not be denied. So similar to the previous rule, the book info and the ingress and nginx namespaces are exempted. Now, of course, we're exempting the ingress nginx namespace even in the previous case because the applications are exposed via that namespace. Okay, so we'd expect to receive inbound traffic from that namespace. Again, we are not permitting that traffic, and when you look at subsequent policies, you will see how traffic from ingress nginx is permitted to workloads that are exposed to external consumers. Okay. However, with this policy, what we've done is similar to the previous policy, isolated tenant2 endpoints from the rest of the cluster. Okay. So the two restrict policies, with the two restrict policies, you create a certain level of isolation. It's a high-level guardrail demarcating those workloads from the rest of the cluster workloads. Okay. All right, so now we have a policy called the front-end policy. So let's go through this policy a bit. This is a network policy, which means it applies to a specific namespace, the namespace being the Hipster Shop namespace. However, in the policy, we're using an endpoint selector. So we're using the selector field and using the app equals frontend label. What this means is that the policy applies only to the frontend endpoints. Okay. In the ingress direction, we're using a namespace selector to select the ingress nginx namespace. However, we're also using endpoint selectors. So we're using the selector field and using an AND operator specifying a couple of labels to match the ingress controller. Okay. So when you're using selectors and when you're using labels, you could use AND or NOT operators. In this case, we're using an AND operator to make sure that the controller has two labels. And that's how we are identifying the ingress controller in this particular rule. Okay. Now in the egress direction, frontend is sending traffic to add service. We specified a port here. Similarly, it's sending traffic to checkout service. Now this rule continues. I've truncated the rule. What's important is not the number of services it's talking to in the same namespace. There's quite a bit of them for this particular application, but the idea being that the pattern is the same. It kind of repeats. And what we're doing is, given that this policy applies to the Hipster Shop namespace, we're using the selector field to select other workloads that the front-end workload can communicate with in the same namespace. Now, bear in mind that just because traffic is permitted from the front-end workload doesn't mean that we've allowed end-to-end communication. Okay. So if you have to visualize this policy, we have the front-end endpoints, and in the ingress direction, we've created a pinhole so that the front-end endpoints can receive traffic from ingress nginx. And on the egress direction, we've created a pinhole so that the front-end endpoints can send traffic to other services in the same namespace. However, for those services, and we'll look at this in a subsequent policy, you also have to make sure that you create an ingress pinhole for those endpoints, okay, which we've not done yet. So just because there's an egress rule permitting traffic from front end to checkout service, it doesn't mean that the rule, or the flow rather, is allowed end to end. All right, so now let's move on to the checkout service policy. Again, this is a network policy which applies to the checkout service endpoints in the Hipster Shop namespace. The policy is a network policy, very similar to the policy we saw for the front-end service. However, if you look at the ingress rule, we are simply permitting the front-end service to talk to the checkout service. So there's a pinhole now created in the ingress direction for the checkout services endpoints. However, if you recall the previous policy, the egress pinhole for the front-end endpoints were created in the front-end policy. Okay. So now with this policy, we now have end-to-end communication, or the end-to-end flow from the front end to checkout permitted. Okay. And the checkout service endpoint has an egress rule, so pinhole in the egress direction for the checkout services endpoint to permitting it or allowing it to communicate with the other endpoints in the same namespace that it should be able to communicate with. Okay. Again, the same logic holds, right? So for example, if it's communicating with payment services, in the policy that we have for payment services, we've got to make sure that that flow is allowed in the inbound direction. Okay. So the policies we're developing for the Hipster Shop namespace are very fine-grained, granular policies, right? The policies apply to select endpoints representing a particular microservice. And for those endpoints, we're applying rules in both the inbound and the outbound directions, right? So these are very granular policies, okay? Now, of course, for the checkout service, we're not permitting traffic from the ingress because it's the front end that communicates, or the front end that receives traffic from the ingress, okay? However, the checkout service will receive traffic from front end and on the egress direction communicate with other microservices or endpoints in the same namespace. All right, so let's move forward. So I've not shown the rest of the policies for the Hipster Shop namespace. Those policies, will continue. However, the pattern remains the same. Okay. So assuming that we've completed the policies for the hipster shop namespace, let's now look at the policy for the Yao Bank namespace. So this is an interesting pattern. So very similar to the front-end policy we looked at, however, with a distinction. So this is a network policy, applies to the Yao Bank namespace. And in the ingress direction, if you look at the rule, given that this policy applies to all endpoints in the Yao Bank namespace, we've not specified a selector. And what that means is all endpoints in the namespace are matched for this policy. If you look at the ingress rule, very similar to some of the ingress rules we looked at previously, we're using the namespace selector and the endpoint selector to select the Nginx ingress controller. However, this particular rule also has a destination field that's used, and the destination for the ingress rule is the customer endpoints. Okay. If you look at the second ingress rule, what this means is that all endpoints in the Yao Bank namespace can receive traffic from all other endpoints in the Yao Bank namespace. Given that this is a network policy and we've not specified selectors, all endpoints can receive traffic from all other endpoints. And the egress rule is similar to that as well. There are no selectors. And what this means is that all endpoints can send traffic to all other endpoints in the Yao Bank namespace. So this is what the pattern looks like. The ingress Nginx can send traffic to the customer endpoints. That's governed by the first rule in the ingress direction. However, the endpoints within the namespace can freely talk to each other since we've permitted or allowed outbound and inbound communications from all endpoints in the same namespace. So this is what this pattern looks like. Now, this is a bit of a coarse-grained policy. At times, you may want to implement such policies, right? If you trust all the workloads inside the namespace, if it's a namespace that is not too critical, however, has several workloads, you can create a guardrail around the namespace rather than for every group of endpoints inside the namespace. Now, this differs from the policy we created for front end and checkout and the services in the hipster shop namespace, because those policies were very specific to a group of endpoints within the same namespace. And even when they had to communicate with other endpoints in the same namespace, it had to be explicitly permitted using rules or policies. All right, so moving on to the bookinfo policy, very similar to the Yao Bank. It's a very similar pattern. Again, traffic from the ingress is permitted, this time to the product page deployment, which is exposed to external consumers, and all communications inside the namespace to and from all the endpoints inside the namespace is allowed. Okay, so very similar pattern to what was seen in the Yao Bank policy. So it's not important that you kind of understand all the microservices involved in some of these examples. The idea is that you understand the pattern, right? So in the Yao Bank example, it was the customer endpoint that was exposed to external consumers. And in the booking, for example, it's the product page endpoints that's exposed to external consumers. And those are the endpoints that have the pinhole in the ingress direction, permitting traffic from the ingress controller. All right, so we've looked at a few policy patterns, right? So we started off with the deny list. We had a pattern for kube-dns, build policies to restrict tenant 1 and tenant 2 workloads. We looked at some granular policies for the endpoints in the hipster shop namespace, and then look at some coarse-grained policies for Yao Bank and bookinfo. And once you're done building policies for a certain set of namespaces, you could then enforce a default deny for those namespaces. So in this case, we're first enforcing a default deny for tenant 1. And what this says is that deny all traffic in the ingress and egress directions for the tenant 1 workloads. This policy is a global network policies, and the workloads are identified using the namespace selector. In this case, we've matched the hipster shop and Yao Bank namespaces. Similarly, we have a tenant 2 default deny, very similar logic. It's a global network policy. We've matched the namespaces using a namespace select. In this case, it's just a bookinfo namespace, and all ingress and egress traffic is denied. All right. So hopefully now you understand the reason for this default deny, right? Sorry, default allow. If you look at this policy model, I have policies where we've matched all the endpoints in the cluster, for example, kube-dns. However, we've not built all the policies for all the endpoints in the cluster, right? And what this means is that if that the default allow wasn't there, right, I would be denying all other flows in the cluster. So the idea being that you take a progressive approach when developing your policy model. You may want to restrict certain environments. So in this case, assuming that the tenants were actually customers, you'd want to secure those custom environments and isolate them from the rest of the cluster. So that's what we've done. And now you can continue with the rest of the policy development. However, hopefully the patterns that we've shown with the global network policies, the network policies, and how environments were isolated from the rest of the cluster, the coarse-grained policies and the fine-grained policies, hopefully those patterns help you think about how you should be approaching policies for your environments. All right, so with the policy model built, now you're in a position, to introduce security policy governance, okay? And when you're thinking about governance, you got to think in terms of a policy model rather than individual policies, and leverage security policy ordering, role-based access control, and admission control to enforce policy governance, okay? For example, if application developers are authoring policies, and if they're authoring policies for a particular namespace, you could, for example, assign a certain order for the policies that they are allowed to author, okay? That kind of ensures that they're not able to circumvent high-level controls that you have enforced. So for example, controls such as the restrict and the deny list may be under the purview of the security team. And when you're permitting other authors to apply policies, you may want to have some governance around that. And policy ordering is a feature that you could use to create a governance structure, okay? Now, of course, policies are Kubernetes resources and as such are subject to Kubernetes RBAC. Again, when allowing other authors to apply policies, you could control which authors can apply policies to which namespaces using RBAC. Of course, tie all of this together with admission control. Alrighty, so there's a lot going on in a Calico policy, and I think we've simply scratched the surface here. The best place to understand all the features, all the capabilities, all the fields and operators available in a Calico policy is to refer to the documentation. I've put the link here to the network policy and the global network policy documentation for Project Calico. All right, with that, I think we're going to wrap this session. Again, thanks for your time. I hope it was beneficial. For more information, you can find us on the Project Calico Slack channel and also the Project Calico documentation for further information around some of the policies and the policy features that we discussed in this session. With that, thanks for watching. I hope you have a good rest of the day. Thank you.
Cloud-native applications can't be secured with the traditional security tools. you need a more active and granular level of security. Calico Cloud is an active cloud-native application protection platform that detects, prevents, and mitigates breaches in cloud-native applications. Let's look at how to secure your cloud-native environment at build time with Calico's container security. At build time, we want to make sure that images that the development team provides are clean and without major vulnerabilities or misconfigurations. All image registries are auto-populated and continuously scanned by Calico's scanning engine. I can also manually add new registries. It's very easy for me to see the results of the last scan from the Scan Results page. Pass-fail is color-coded with specific scores. Details about each vulnerability that impacts each image are available on the right side. I can control which images can be displayed to my environment using admission control policies. I am only allowing images with pass or warn scan results. I've also enforced an upper limit for the age of a scan result. Now, if any application developer attempts to deploy an image that doesn't pass the security criteria, it will automatically be blocked. Once you have the admission policies in place, you may come across a situation where the application developer is telling you that a particular vulnerability does not impact their code and the way in which they are using the affected library. In this case, you need to create an exception. Calico Cloud offers a number of options to scope the exception to a specific image version, any version of this image, or any image. In addition to scanning and assessment of images, I must ensure the Kubernetes environment is also secure and does not have any misconfigurations. Calico helps you continuously assess your Kubernetes configuration using compliance reports that assess your configuration against CIS benchmarks. I scheduled my CIS benchmark report to run every 24 hours. The number of nodes passing or failing the CIS benchmark tests is color-coded. And here are the top failed tests. I can also download the full report to get more insight on each test and how to mitigate its risk. At this stage, I have scanned all my images, allowed the deployment of only those that pass the security requirements, and I have also assessed my deployment environment against CIS benchmarks. Try it yourself by signing up at www.calicocloud.io. Cloud-native applications can't be secured with the traditional security tools. You need a more active and granular level of security. Calico Cloud is an active cloud-native application protection platform that detects, prevents, and mitigates breaches in cloud-native applications. Let's look at how to secure your cloud-native environment at build time with Calico's container security. At build time, we want to make sure that images that the development team provides are clean and without major vulnerabilities or misconfigurations. All image registries are auto-populated and continuously scanned by Calico's scanning engine. I can also manually add new registries. It's very easy for me to see the results of the last scan from the Scan Results page. Pass-fail is color-coded with specific scores. Details about each vulnerability that impacts each image are available on the right side. I can control which images can be displayed to my environment using admission control policies. I am only allowing images with pass or warn scan results. I've also enforced an upper limit for the age of a scan result. Now, if any application developer attempts to deploy an image that doesn't pass the security criteria, it will automatically be blocked. Once you have the admission policies in place, you may come across a situation where the application developer is telling you that a particular vulnerability does not impact their code and the way in which they are using the affected library. In this case, you need to create an exception. Calico Cloud offers a number of options to scope the exception to a specific image version, any version of this image, or any image. In addition to scanning and assessment of images, I must ensure the Kubernetes environment is also secure and does not have any misconfigurations. Calico helps you continuously assess your Kubernetes configuration using compliance reports that assess your configuration against CIS benchmarks.